Hi, my name is Darshan and I'm a private tutor of math and physics. In this video, we'll talk about AP Physics 1 2023 FRQ question number 1. It's an interesting question based on the simple harmonic motion. The question is right in front of you. So let's read this out. It says that a cart on a horizontal surface is attached to a spring. So this is the cart and this is the spring which is attached over here, and the other end of the spring is attached to a wall. So this is wall over here and the spring is attached to it. The cart is initially held at rest as shown in figure 1, and when the cart is released, the system consisting of the cart and spring oscillates between the points plus L and minus L. So clearly that's a simple harmonic motion of the spring mass combination oscillating between negative L and plus L, of course. In figure 2, it shows the kinetic energy of this cart spring system as a function of the spring's potential energy. So that's interesting. They have graphed the kinetic energy versus the potential energy, and it particularly is a linear curve with a negative slope. Friction forces are negligible. On the graph of the kinetic energy versus the potential energy shown in the figure 2, we have to, the values of the x and y intercepts are same. Of course, we can clearly see y intercept is also 4, x intercept is also 4. So they're asking us to justify this using the physics principle. I think the justification is pretty straightforward because there are no frictional forces, right? So can we say that there are no non-conservative force? So we can say that the non-conservative forces are equal to 0. And if there are no non-conservative forces, can I also say that the mechanical energy of the system is conserved, right? The mechanical energy of the system is conserved. So it makes absolute sense that at when the kinetic energy was 4, and can you remind me when is the kinetic energy maximum? Is that at extreme mass or is that at equilibrium? At equilibrium, not an extreme mass, because at extreme mass the speed is 0 and the amplitude is maximum, and at the equilibrium, as in at x equal to 0, the amplitude, I mean the elongation is 0, so the displacement is 0 while the velocity is maximum. So this k equal to 4 joules corresponds to the point of x equal to 0, and this 4 joules of potential energy corresponds to the point of either extreme mass. So it makes absolute sense that their intercepts are same, because it indicates that whatever kinetic energy was at the equilibrium, that same kinetic energy got converted completely into the potential at the extreme mass, because mechanical energy is conserved. So that is the reason why the kinetic energy and potential energy curve has the same intercepts. I hope that makes sense. Let's jump on to question number part B of the same question. Oh, this is interesting. They are pretty much mixing momentum in SHM. When the cart is at plus L and momentarily at rest, this is really important, momentarily at rest, a block is dropped onto the cart as shown. We can clearly see that a 3m0 block is dropped on the block m0, and the block sticks to the cart, and the block cart spring system moves and continues to oscillate still between negative L and L, right? So amplitude doesn't change. The masses of the cart and the block are m0 and 3m0 respectively. That's fine, we can see it. If the frequency of oscillation before the block is dropped onto the cart is f1 and after it is dropped is f2, then what is the numerical value of the ratio of f2 over f1? Let's remind ourselves, what is the formula for the frequency of spring mass system? Well, I do remember the formula for the time period. It's 2 pi root m over k. So obviously the frequency is just going to be 1 over t, right? So it's 1 over t, which is 1 over 2 pi root of k over m, because I just took the reciprocal, right? So 2 pi came at the denominator and m over k became k over m with a square root over it, right? So this is the usual formula for the frequency. So what is the frequency f1? F1 is simply when m is m0. So F1 is 1 over 2 pi root of K over m naught. And what is the value of F2? So in F2, nothing changes except the mass, because the total mass which is oscillating now is 4m naught. So the F2 will now become 1 over 2 pi root of K over 4m naught, not 3m naught, because the total mass will be obviously 4m naught. So this is 4m naught over here. It's good to see 4 because square root of 4 is 2, right? So I'm going to write this as 1 over 2 pi times 1 over 2. Why the 1 over 2? Because the square root of 4 is 2. And then root of K over m naught remains as it is. All right. They need the ratio of F2 over F1. So that's what we're going to do. F2 over F1 is going to be there you go. In fact, there is a better way to find the ratio. In fact, we can do it like that as well. Doesn't really matter. So F2 is 1 over 2 pi times 1 over 2 times root of K over m naught over F1 from here is 1 over 2 pi times root of K over m naught. If we notice carefully, 1 over 2 pi and 1 over 2 pi is gone. Root of K over m naught and root of K over m naught is gone. All we are left with is 1 over 2, which is or should be our final answer. So F2 over F1 is 1/2. That should be the answer to this question. All right, let's move on to the next part. Here they say that the dashed line in figure 4 shows the kinetic kinetic energy versus the potential energy of the block card system after the block is dropped onto the card. So even after dropping, their energy is not changing. That's interesting. This graph is identical to the graph, of course, for the card spring system before the block is dropped. So we have to explain that why they are same using the physics principles. So that's same because if we go back, right at the time when it is dropped, we know that the momentum should be conserved, right? So if it is conserved, the initial momentum should be equal to the final momentum. Notice carefully over here, what do they say? They say that when it is dropped, m naught was at rest. It means that after dropping 3m naught as well, the system should be at rest, so that the initial momentum is 0. And right after dropping, the final momentum should be 0. So its speed or the velocity should be 0. Okay. So if its velocity is 0, and since this is the extreme point, what is the only energy in this particular system? Isn't that just potential? Because the potential energy is spring potential is K over 2 x naught square. And what is x naught? X naught is L, because this thing happens at x equal to L. So don't you think still after dropping, just at that instant, the total energy is K over 2 times L square? And isn't this same as the previous one, where it's still the potential energy is K over 2 L square, which has a value of 4 joules, right? So that is the reason why the total energy is still 4 joules. And since still the mechanical energy is conserved, because there is no external force. Obviously, the friction is already being ignored. They are already saying that you have to ignore the friction. So there is no non-conservative force. Mechanical energy is conserved. Since amplitude remains same, momentum is conserved. At the extremas, the energy is same as the previous one, and hence the total energy just remains the same. That is the justification of why the two curves are identical in this particular case. There's another way in which you can explain it. The maximum velocity, if we remember the formula, is omega times a, right? Okay. Now, what is omega? Omega will change, right? Omega is root of K over m. So it's K over 4m naught, because the total mass is now 4m naught, and amplitude is still the same. So what is the maximum kinetic energy at the equilibrium? Obviously. So K max is going to be half m. This is where we have to be careful. Half mv square. And what is m? M is 4m naught, And if we do v square, we have to do root of k over 4 m naught times a whole square. So if we open this up, this becomes half of 4m naught times k a square over 4m naught. And fortunately, 4m naught and 4m naught is still cancelled, and we once again end with 1 over 2 k a square, which is nothing but what we got over here, because amplitude is obviously L, so I can replace amplitude with L, and we can clearly see that these two energies are still same. So either you can justify using the, obviously because AP Physics 1, they go with the rubric and everything is stepwise marking. So if you want to show the math, obviously you can do this and you will get full credit. Otherwise you can write it as a qualitative fashion, or whatever I have said, the justification, along with mechanical energy conservation and all of that. Still you will get the full credit, right? So this is how we can answer this particular question. I hope it makes sense. Let's go to, I think this is the last part. So this is the, in fact, this is part C, part 2. Okay, after the block is dropped onto the cart, consider a system that consists only the cart and the spring. So no cart and the spring, as in not the block. What is the block? If you are getting confused, a block is dropped. This is the block, right? This guy is the block. Let me highlight that with a different color. This guy is block. So now they are asking us to ignore the block, right? They are asking us to treat only m naught and the spring as a system. All right, okay, we can do that. So only the cart and the spring is our system now. And on figure 4, as in on the same figure, sketch a solid line that shows the kinetic energy of the system that consists of the cart and the spring, but not the block after the block is dropped onto the cart. This is a really interesting question where we are going to borrow the work which we have done earlier, because we know that the maximum speed is this. However, what is the maximum kinetic energy just of the cart spring system? Because at equilibrium, obviously there is no spring energy, right? It's the maximum kinetic. So if we now find the value of the maximum kinetic energy, that's going to be half. Now the mass will be m naught, because remember we are only taking the cart, not the block, and the block was 3m naught, which is ignored. So m is still m naught, while v remains same, right? Because both the cart and the block have the same velocity. And we already found in the previous question, it's this one. So I'm gonna write that over here, k over root of k over m naught times what was that, a, and a is L, right? Amplitude, so that's square. So this is gonna be equal to half m naught k over 4 m naught L square. M naught and m naught is gone, so we are left with 1/8 of KL square. Actually, there is a better way to write this, to understand this intuitively. I'm going to write that as 1/4 of 1/2 KL square. Why? Because this makes a clear sense that now the maximum energy is 1/4 of the initial energy, because half KL square was the initial energy, right? Here, there you go. This is the initial kinetic energy. So this is 1/4 of the initial kinetic energy maximum. And do you think the maximum potential will change even if we change our system to cart and spring? No, because the maximum potential is only dependent on the spring, and the spring is still a part of the system, right? It's still a part of the system. So the maximum kinetic energy will still be, maximum potential energy will still be a 1/2 KL square, since the spring is still a part of the system. However, the maximum kinetic energy will now be only 1/4 of the initial. What was the initial? 4. What is 1/4 of 4? It's 1. So the solid line is going to look like this. It starts from 1 now, and it still goes to 4. So this is how the kinetic energy versus the potential energy of the cart spring system is going to look like. I hope this question makes sense. It was not difficult, entirely conceptual. I will soon post a video on question 2, FRQ 2 of AP Physics 1 2023 exam. Stay tuned for that and please subscribe to my channel. Bye-bye.